A very good afternoon. Welcome to the Selection Hour. I am Neha Gupta. In today's class, we will be mixing a few questions with theory. So, previously we were doing group 16 elements, that is the oxygen family. So, firstly, we'll finish the topic that we were doing, that was reactivity. We had already covered reactivity with hydrogen, that is the formation of hydrides. Now, after that, we'll be doing the reactivity with oxygen and reactivity with halogens. And upon covering these topics, we'll do a few questions that have come in the previous year's papers. So, talking about reactivity with oxygen, all the group 16 elements, sulfur, selenium, tellurium, and polonium, react with oxygen to form two types of oxides, EO2 and EO3. So SO2, SO3. And if you talk about oxygen, oxygen also has another allotrope, which is O3. So O3 is a gas. SO2 and SO3 are also gases. All these oxides, EO2 and EO3 types, are acidic in nature because all these elements are non-metallic. This one is a definite non-metal, and these ones are weakly non-metallic in nature. So all these are acidic in nature. If you talk about the reducing property of the dioxides, it decreases from SO2 to TeO2. So if we write SO2, SeO2 and TeO2, we're talking about the reducing behavior. If SO2 is reducing, this would mean that it's in the +4 oxidation state itself, it would get oxidized to a +6 state. On moving down the group, what happens? This is reducing. TeO2. Tellurium does not want to come into a +6 state because we discussed earlier also, when we come to tellurium, we are moving across a period also, and we are moving down a group as well. Because we have moved across a period, the size of tellurium has become very small, and because of that reason, +6 state is not that stable with tellurium as it would have been. So that is the reason TeO2 is an oxidizing agent. Now, before we proceed, there was a slight confusion in the last class which I need to clear. So we were talking about the anomalous behavior of oxygen, where we talked about the p-pi bonding. So p-pi bonding takes place in oxygen because it is small in size, it is highly electronegative. So strongest p-pi bonds are formed in oxygen. So if we compare the carbon compounds of group 16 elements, carbon dioxide, carbon disulfide, carbon diselenide, carbon ditelluride. All right. So here they are discrete CO2 molecules, and this is a gas. Okay. There are strong p-pi bonds. In CS2, weak p-pi bonds are formed. CES2 does not form p-pi bonds. It forms single bonds and hence long chains. And CTE2 does not exist. All right. Now moving on to the reaction with halogens. Reactivity towards halogen. So if we talk about oxygen, the only element that is more electronegative than oxygen is fluorine. So the molecules, the compounds that are formed with oxygen fluorine are OF2 and O2F2, which are not called oxides of fluorine, they are rather fluorides of oxygen, because fluorine is more electronegative. With the rest of the halogens, let's say OCl2 is formed, O2Cl is formed. These are all oxides of chlorine. So the difference only lies here in the reaction with fluorine. Now coming to the rest of the elements, all of them are less electronegative than the halogens. Rest of the elements form halides of the type EX6, that is a hexahalide, EX4 tetrahalide, EX2 dihalide, and a monomeric also forms EX, which always exists as a dimer. The stability of these halides decreases in the order F. Halides with fluorine are the most stable. Halides with iodine are the least stable. Because the size increases, the bond length also increases. All hexafluorides, now let's talk about the hexafluorides. They are gaseous in nature. So the most stable hexafluoride is SF6. If we talk about SF6 for sulfur, this is the valence shell electronic configuration. To form a hexafluoride, all these electrons need to get excited. So the excited state here would be this. This is 3s, this is 3p, and this would be 3d. 1, 2, 3, 4, 5, 6. So these two electrons here got excited to the 3d level. Alright. And now fluorine will form a bond here in all these orbitals. One electron from each fluorine atom, giving us sp3d2 hybridization. So in sp3d2 hybridization, the structure of SF6 would be this one here, which is octahedral. So this will have an octahedral structure. So all hexahalides will have an octahedral structure. Among the tetrafluorides, SF4 is a gas, SeF2 is a liquid, and TeF4 is a solid. That is expected because on moving down the group, size increases, the van der Waals forces of attractions are also increasing, hence gas, liquid and solid. So if we talk about tetrafluorides like SF4 or TeF4 or TeCl4, for a tetrafluoride to be formed, one electron from here gets excited to the 4d level or the 5d level of tellurium, and the shape of the molecule here would be this, with one equatorial position occupied by this lone pair. So this is also called a seesaw shape. And the geometry, trigonal bipyramidal. If we talk about the dihalides, the most important dihalide is SCl2. Now SCl2 is used for the preparation of mustard gas, if you have heard. First, if we talk about the geometry, it is sp3 hybridized tetrahedral geometry with two positions occupied by lone pairs. Alright, so it is a bent molecule, an angular molecule. Now SCl2 has a unique property that it adds on very quickly to double bonds. So SCl2 adds on to ethene to give this compound CH2CH2Cl, which is called mustard gas. This is it's a lethal gas. It was used in World War I. It was even used in the Iran-Iraq war. So this gas is a liquid, a volatile liquid, which is sprayed on the ground and it is blown away by the winds towards the enemy. So what happens? In living cells, this is converted to a divinyl compound which disrupts the structure of the protein. So it causes severe blistering and death. So SCl2 is used for the preparation of mustard gas. Sorry. Right. So now it says all elements except oxygen forms dichlorides and dibromides. This we have already discussed because oxygen is more electronegative than chlorine and bromine. Alright, the dihalides are formed by sp3 hybridization. Now the monohalides are always dimeric in nature. This is because the monohalides, let's say SF, would be an odd electron molecule. Because it's an odd electron molecule, it is always formed as a dimer. So these are the dimers of the monohalides. Now these monohalides, these dimeric monohalides undergo disproportionation, such as this particular reaction here. So Se2Cl2 undergoes disproportionation to give SeCl4, where Se is in a +4 state, and Se where Se is in a 0 oxidation state. So this is about the reactivity. Now coming to a few questions which have come in the previous years from these. Alright, so this question is from the reactivity with hydrogen, or it is from hydrides. Given below are two statements. Statement 1, the boiling point of the following hydrides of the group 16 elements increases in the order. So the order that they have given is this. Statement 2 says the boiling point of these hydrides increases with increase in molar mass. So here the problem lies in both the statements. What happens in hydrides? The boiling point and the melting point of water is anomalous because of the presence of hydrogen bonding. So if you look from H2S to H2SE to H2TE, you will see that because van der Waals force is increasing, boiling point would increase with the increase in molar mass. But in the case of water, what happens? The boiling point is higher. So this is the actual order that is followed, and this statement is not really observed because of hydrogen bonding. Hence, the correct answer would be both statement 1 and 2 are incorrect with respect to group 16 elements. Okay? Because they are saying of these hydrides. It is not a general statement. They are giving the second statement with respect to these hydrides. मतलब group 16 के hydrides के लिए वो कह रहा है कि molar mass increase होगा तो boiling point increase होगा, but ऐसा नहीं होता. This is the anomaly here. Hence, both the statements are incorrect. Next question. In which one of the following arrangements the given sequence is not strictly according to the properties indicated against it? Not strictly. The first one is HF, HCl, HBr, HI, the increasing acidic strength. So this is correct because what happens on moving, this is group 17. On moving down the group, the bond length is increasing and hence it is easier to furnish a proton in HI compared to HF, and hence this statement is correct. Now, second is H2, H2S, H2SE and H2TE in increasing pKa values. So they're again talking about acidity. The difference is they're talking about pKa. So pH is minus log of pKa. So large pKa means less acidic. Alright, now what happens in the group 16 hydrides? On moving down the group, the bond length increases. The bond dissociation enthalpy of the element with hydrogen decreases, the bond length increases, hence acidity increases. So this is the trend of acidity, acidic strength or acidity. But this is not the trend of pKa because it has inverse logarithmic relation. So this is again not true. So answer would be this one. Let us look at the other ones. They are talking about group 15 now, NH3, PH3, arsenic hydride and antimony hydride, increasing acidic character. Now they are saying acidic character, but we have studied the basic character. So since these hydrides are Lewis bases and ammonia is the strongest Lewis base, hence the reverse would be true for the acidic, Lewis acidic character of these hydrides. Coming to the last option, increasing oxidizing nature or oxidizing power. So this is carbon dioxide, silicon dioxide, and so on. So in this carbon family, this is in a +4 state. What happens on moving down the group? The stability of the +4 state increases, right? And that of +6 decreases. So if CO2 is an oxidizing agent, that means its oxidation state needs to decrease. But here, this order is true because +4 would not want to go to a +6 state, +4 would want to get to a reduced state. So this order is also correct. So not strictly following is this particular one, option B. Next question is, which is the correct thermal stability order for H2E? Again, group 16 hydrides. Thermal stability would mean how stable it is with respect to temperature. So on moving down the group, the EH bond length increases. Okay, that means the stability decreases on moving down the group. So here, the correct thermal stability order, this is H2O, H2S, H2SE, H2TE, H2PO. So this one is the least stable on moving down the group, and H2O would be the most stable. Okay, so out of these order, you will see which one is true. Option B here, where they are saying H2 is the most stable and H2PO is the least stable. So this is the correct order, option B. Acidity of diprotic acids in aqueous solution increases in the, this is a repetition again. So on moving down the group, the acidity increases. So the correct option would be this one here. Sulfur, selenium, tellurium. So on moving down the group, acidity increases. All right. Now coming back to our topic, we had done reactivity. The next topic under group 16 elements is the allotropes of oxygen. So oxygen exists as two allotropes, dioxygen and ozone. So dioxygen is O2. This is a colorless, odorless gas, and in liquid it is pale blue in color. So pale blue liquid. The solubility of oxygen is just enough to support the aquatic and marine life. So the amount of oxygen that dissolves in water is just the right amount. It is most perfect. Now what happens? Oxygen reacts with almost all elements, but apart from a few like noble metals and noble gases like gold, platinum, tungsten, and the noble gases. So it reacts directly nearly with all metals and non-metals except some metals, these one here, and the noble gases. To initiate the reaction with dioxygen, first we need to break up the molecule. So O2 needs to be broken into oxygen atoms, and then energy needs to be provided to continue the reaction. But in the case of oxygen, what happens? All the reactions are exothermic, that is, they are strongly energy releasing. So a lot of energy is released when any element reacts with oxygen. Hence, so whatever energy is required to dissociate the bond is compensated by the energy that is released, and the reaction continues spontaneously. It moves on its own. So these are the reactions of oxygen with various metals and non-metals. So with calcium, it gives calcium oxide. Aluminium and oxygen gives aluminium oxide. Phosphorus with oxygen gives P4O10. C and O2 gives CO2. It also reacts with some sulfides. So zinc sulfide with oxygen gives zinc oxide. Methane with oxygen burns to give CO2 and H2O. This reaction is true for all alkenes as well as alkynes. Now some compounds are catalytically oxidized. They don't react with oxygen that fast. To speed up the reaction, a catalyst is required. So this particular reaction here is very important. We'll study this in the contact process for the manufacture of H2SO4. Here, SO2 reacts with oxygen in the presence of V2O5 as the catalyst to give SO3, sulfur trioxide. Another reaction which is catalyzes HCl reacting with O2 in the presence of CuCl2 catalyst to give Cl2 and H2O. So these are the reactions of oxygen with various metals and non-metals. Coming to the preparation of dioxygen. Oxygen is the most abundant element present on the earth in combined form as well as in its molecular form. Now, majority of this oxygen is prepared by photosynthesis. Okay, so chlorophyll uses sun's energy and CO2 and water to produce glucose, foodstuff like glucose and oxygen. So most of it is produced by photosynthesis, but in the lab you can prepare it by all these methods. The first one is by heating oxygen containing salts such as chlorates. So KClO3, potassium chlorate on heating with MnO2 gives KCl and O2. Nitrates, so if we have KNO3 on heating, it would give KNO2 and oxygen. And permanganates, KMnO4 on heating gives K2MnO4 plus MnO2 plus O2. So these are the preparation methods of preparation in the lab. Now it is also found that thermal decomposition of the oxides of metals, okay, and higher oxides of some metals. So silver oxide on thermal decomposition gives silver and oxygen. With mercury, it's the same case. HgO gives Hg and oxygen. Higher oxides of lead on thermal decomposition gives PbO and O2. This is a mixed oxide of lead. We'll just talk about it shortly. Third method is from hydrogen peroxide. So hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. So hydrogen peroxide also gives dioxygen. On a large scale, it can be produced by electrolysis of air or water, and the last industrial method is by fractional distillation of air. So from air, first all water vapor and carbon dioxide is removed, and then only nitrogen and dioxygen are left, which are fractionally distilled because there is a difference in their boiling points. Coming to the properties, we have already talked, it's a colorless, odorless gas. It has 3 stable isotopes, O16, O17 and O18. Now a very important thing about oxygen is that it is paramagnetic. Despite being, it is not an odd electron molecule, okay. So O2 contains 16 electrons. 16 electrons means all electrons should be paired. Why is it so that O2 is paramagnetic? Let us see how. If we write the molecular orbital configuration of O2, total 16 electrons, sigma 1s, sigma 2s, sigma sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma px, pi 2px, pi 2py, pi 2pz, pi star 2py, pi star 2pz. Now if you start filling up the electrons, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 electrons filled up till here. Remaining 2 electrons come here. So the anti-bonding orbitals are singly occupied. That means they are unpaired electrons. And it is for this reason that O2 is paramagnetic. Now if we talk about the bond order, it is calculated by number of bonding electrons minus number of non-bonding electrons divided by 2. So for oxygen, the bonding electrons are these and these, right? So 4, 6, 10. 10 minus 6 divided by 2. So this is how we calculate the bond order. Now, higher the bond order, more is the bond strength. More stable is the species. Right? This is the trend that is followed. Now, coming to a question that occurred in the previous year's papers. Here. So you have to tell the decreasing order of stability of these species. Decreasing order would mean max stable to least stable. So how will you go about solving this question? Just like we determined the paramagnetic nature of O2, you will write the molecular orbital electronic configuration of all these species. So O2 has 16 electrons, O2 minus has 17 electrons, O2 plus will have 15 electrons, and O2 2 minus will have 18 electrons. And for each of these species, you calculate the bond order. So bond order is calculated. Higher bond order would mean more stable. So that is how you find out which one of these species is more stable. So you calculate the bond order using the MO theory. All right. So this is how we do it. Now coming to the oxides. Since oxygen reacts with almost all metals and non-metals, all right, so it forms a variety of oxides. These oxides can be categorized to 3 categories. The first category is simple and mixed. So what are simple oxides? Simple oxides are oxides like Al2O3, Na2O, H2O. What is happening here? Only one type of cation is present in one oxidation state. That is a simple oxide. In mixed oxide like Pb3O4 and Fe3O4, here the cation is lead, but lead is present in 2 different oxidation states. So this is made up of PbO and PbO2, and Fe3O4 is made up of Fe2O3 and FeO. So here iron is in 2 oxidation states, +3 and +2, and lead is in 2 oxidation states, +2 and +4. So these are mixed oxides. The second categorization is based on the geometrical structure. The first category is normal oxide. So in normal oxide, simple MO bonds are formed, where M is any element. Alright, so whatever oxides we have studied till now in the reactions of oxygen with metals and non-metals, all these are normal oxides. BaO, CaO, H2O, Na2O, MgO. Okay, here you can find out the oxidation number of the metal or the non-metal by taking the oxidation number of oxygen as -2. Okay. In the case of peroxides, what happens? More number of oxygen atoms are present than you can deduce from the oxidation number of the metal. So here they are of two types, ionic and covalent. An example of ionic peroxide is Na2O2. So from the oxidation number of oxygen as -2, you cannot determine that there are 2 sodium atoms. Alright. Now here, because it's an ionic peroxide, it contains O2 2- species. Covalent peroxides contain this type of linkage. 2 oxygens attached by a single bond. So an example of covalent peroxide is H2O2. These are peroxides. Now the third category here is a suboxide. What happens in the case of a suboxide? Suboxide has less number of oxygens than can be deduced, than can be found out from the oxidation number of the metal or the non-metal. So here, apart from MO bonds, like in normal oxides, there are MM bonds also present, like in the case of C3O2, which is an oxide of carbon. The structure of C3O2 would be like this. So this is a suboxide. The third and the most important classification, because it comes in every group, is the classification based on acidic and basic properties. Now, if I write 2 oxides, calcium oxide and carbon dioxide, this is a metal oxide, this one is a non-metal oxide. So the combination of these two gives me Ca2 plus and CO3 2-. So what exactly is happening here? This metal oxide gives an oxygen and forms Ca2 plus, gives oxygen, and this non-metal oxide accepts an oxygen and forms CO3 2-. So the oxide which gives an oxygen, according to the Lux-Flood definition of acidity and basicity, the oxide which gives an oxygen, a metal oxide, is a basic oxide, and the oxide which accepts an oxygen is an acidic oxide. Right? Basic oxides are all metal oxides, right? So metal is highly electropositive. That means basic oxides are formed by an electropositive and an electronegative element. So mostly these are ionic in nature. For the formation of a basic oxide, what is happening? Calcium, let's say, or any electropositive metal has to react with oxygen O2. Now to react with the oxygen, first step is breaking of the double bond between oxygen. Alright, so first energy is required to break that bond. Now we have 2 atoms of oxygen. To form O2 2- species, which is present in a metal oxide, oxygen needs to gain 1 electron. So that is the first electron gain enthalpy, which is negative. Then oxygen needs to gain another electron to form O2 minus. All right. The electron gain enthalpy for addition of a second electron to oxygen is very high. It is positive. So only those oxides with metals are formed which have a high lattice energy. Why is that so? Because a lot of energy is required for the formation of O2 minus, we need some energy that compensates for this fact, right? So since initially a lot of energy is required, once the crystal is formed or once the ionic compound is formed, a lot of energy is produced if the compound has a high lattice energy. That high lattice energy compensates for the energy required for the production of O2 minus. O2 minus. All right. So hence this means all ionic compounds, since they have a very high lattice energy, ionic compounds of metals with oxygen, they have a high melting point also. Now some metal oxides like M2O3 types do not dissolve in water. Okay. So all these basic oxides like calcium oxide on dissolving water give a base, calcium hydroxide. So the O2 minus species in water gives us OH minus and a base is formed. This is true for all the basic oxides. But some metal oxides like M2O3 do not dissolve in water. In such cases, they react with acids to give us salts. So now that means to categorize any oxide as acidic or basic, one, we know all metal oxides are basic oxides. Second, any oxide which gives us a base with water is a basic oxide. Third, if it does not dissolve in water, any oxide which reacts with acid to give us a salt is a basic oxide. Now coming on to the non-metal oxides or the acidic oxides. Non-metal oxides or acidic oxides. Non-metal oxides like N2O3, N2O5, SO2, SO3 and so on, all of them react with water to give us an acid. So N2O3 gives HNO2, N2O5 with water gives HNO3, SO2 with water gives H2SO3 and SO3 with water gives H2SO4. All these are acids. So oxides which give us an acid in water are non-metal oxides. All non-metal oxides are covalent in nature. Right? That means they have low melting and boiling points compared to the ionic oxides. We can safely say that majority of the non-metal oxides are anhydrides of acids also. Now some non-metal oxides like SiO2 do not react with water. Okay. So they react with bases to form silicates or a salt, and hence we come to know that since it's a non-metal oxide, it is reacting with a base to give us a salt. That is the reason SiO2 is also a non-metal oxide. Not all non-metal oxides will react with water. So they react with a base to give us a salt. Another important thing about SiO2 is all non-metal oxides are covalent with low melting and boiling points, but Si2 has a very high melting point and melting point. That is the reason, because it is the reason behind it is a 3D solid. So their bonds extending in all directions. So it is a 3D network and it is a solid, and hence its melting point is high. Otherwise, all non-metal oxides are covalent in nature and they have low melting and boiling points. Apart from this, Non-metal oxides are acidic, but oxides of some metals in a high oxidation state also have acidic character. So if you are comparing oxides of the same element in different oxidation states, okay, like N2O3 and N2O5. So the oxide in the higher oxidation state will always be more acidic. Or we can say that the oxide in the lower oxidation state will be more basic. Because lower oxidation state would favor the formation of an ionic compound, and an ionic oxide is a basic oxide. This is from Fajan's rule. All right. Apart from acidic and basic oxides, we have amphoteric oxides. Amphoteric is the oxides which show the property of both acidic oxides as well as basic oxide. That means they react with both acids and bases. So an example of amphoteric oxide is Al2O3. Al2O3 reacts with acids with HCl like this, and it also reacts with base like NaOH. Alright, so this is an amphoteric oxide. Apart from these, the fourth category is neutral oxides, which react with neither acids nor bases. So that's carbon monoxide, nitric oxide and nitrous oxide, CO, NO and N2O. So these are the oxides. Now the next allotrope of oxygen is ozone, O3. O3 is a triatomic molecule and it is too reactive to remain in the atmosphere at sea level. So it is present 20 kilometers above our surface as the ozone layer, and it absorbs very strongly in the UV region. Because of that, it protects us from harmful UV rays of the sun. If we talk about the preparation, when a slow dry stream of oxygen is passed through a silent electrical discharge, oxygen gets converted to ozone. So here this particular reaction is very important. So what do you see? The reaction of conversion of oxygen to ozone is endothermic. Right? So if we do not use a silent electrical discharge, a silent electrical discharge would mean a sparkless discharge which produces less energy, less heat energy. Because if a lot of heat is produced, then ozone would decompose back to oxygen, since this reaction is endothermic. This is the method of preparation. So to prevent its decomposition, a silent discharge is used. We talk about the structure of ozone. It contains one pi bond and two sigma bonds. These are the two resonating structures, and the central oxygen is sp2 hybridized, and this pi bond is delocalized over the entire molecule. Now, ozone has a characteristic smell, and in small concentrations it is harmless, but if the concentration increases above 100 parts per million, breathing becomes very difficult, okay, and it causes headache and nausea. Now, ozone is thermodynamically unstable with respect to oxygen, okay. This can be inferred from this particular reaction here. So because the conversion of oxygen to ozone is endothermic, that means it is less stable thermodynamically compared to oxygen. So if we take the reverse reaction, that is 2 moles of ozone giving us 3 moles of O2, the delta H now becomes negative. All right, and in this case the number of moles of gas is increasing, so delta S is also positive. So if we talk about delta G, which means delta H minus T delta S, this becomes a big negative term. That means for this particular reaction of conversion or decomposition of ozone to oxygen, delta G is negative. Right? This is the reason in high concentrations, ozone can be dangerously explosive and it can get converted to oxygen. Now, there's another interesting property of ozone, that it acts as a powerful oxidizing agent because of the ease with which ozone gives a molecule of oxygen plus nascent oxygen. So nascent oxygen is an atom of oxygen which has not yet reacted with anything. So ozone easily gives us O2 and O, and because of this it acts as a powerful oxidizing agent. So the two oxidation reactions of ozone are, it oxidizes PbS to PbSO4 and gives oxygen. Another interesting reaction is where it oxidizes I minus to I2, iodine solid. Now this is the particular reaction which is used in the estimation of ozone using titration. So the quantitative method for estimating O3 gas is based on that oxidizing property of ozone. So what happens? We have an aqueous Ki solution which is buffered with a borate buffer and the pH is at 9.2. Ozone is passed through the aqueous Ki solution. So we have O3 passing through the aqueous Ki solution. This gives us KOH, O2 and I2 because ozone now oxidized I minus to I2. So I2 gets formed here. To this we add a starch indicator. Starch forms a blue complex with iodine. So now the liquid in the titration flask is blue in color. To this we add sodium thiosulfate. S2O3, Na2S2O3 is sodium thiosulfate. We titrate this iodine with the starch indicator with sodium thiosulfate. So now what happens? Iodine with S2O3 2 minus, this acts as an oxidizing agent and this oxidizes S2O3 to S4O6 2 minus, that is a tetrathionate ion, and it gives us I minus. So once all the iodine has dissociated back to I minus, the blue color with the starch will disappear because starch only gave a blue color with iodine. Once all the iodine is converted to I minus, the blue color will disappear, and that is the end point of the titration where no longer there is a blue color and the solution is colorless. So that is the end point, and this is the method by which O3 gas is estimated quantitatively. Now there are two consequences of depletion of our activities, human activities, which is leading to the depletion of the ozone layer. One is the extensive usage of freons or chlorofluorocarbons. So the chlorine in chlorofluorocarbons at a very high level where ozone is in the atmosphere breaks down into chlorine radicals in the presence of sunlight, and that leads to decomposition of ozone. Secondly, nitric oxide, which is emitted by supersonic jets, also depletes ozone via this reaction. So with ozone it forms NO2 and O2. This also leads to decomposition of ozone into oxygen. Alright, so because of these two, freons and nitric oxide, there is a threat to ozone layer. Alright, another threat possessed by use of freon. We have already discussed the structure. So the two oxygen-oxygen bond lengths are identical, and that is because they are identical because the pi bond is delocalized over the entire molecule. Alright, coming to the next topic, that is the oxoacids of sulfur. Oxoacids of sulfur is extremely important from NEET point of view. So the important oxoacids of sulfur are these. In your book, only 4 of these structures are given, but we will discuss all of them one by one. So H2SO3, H2 H2SO4 and H2S2O5. These three are the sulfurous acid series. Then we have H2SO4, H2S2O7 and H2S2O3. These three are the sulfuric acid series. This one here, H2SXO6, where X ranges from 2 to 5, is the thionic acid series. And H2S2O8 and H2SO5 are the peroxo acid series. All right. So what happens in the peroxo acid series? In these two compounds here, this is peroxo monosulfuric acid, and this is peroxo disulfuric acid. Since they are peroxo acids, they will contain this linkage. All right. So if we draw the structure, one of them is there in your book, H2S2O8. So you will see that between two sulfurs there is an OO linkage. So this is the structure of peroxo disulfuric acid. So this sulfur is tetrahedrally bonded, two bonds of sulfur double bond oxygen. Here also two S double bond O, one SOH, one SOH here, and both of them are bridged by a peroxo bond, like two oxygens. Okay. If we talk about peroxo monosulfuric acid, which is also called Carro's acid, its structure is like this. So it also contains O linkage, and then it is bonded to a hydrogen. Since there is only one sulfur, we have three more oxygens. One is an SOH bond and the others are S doubly bonded to oxygen, like this. So this is peroxo monosulfuric acid. Sulfurous acid series, H2SO4, this is called sulfurous acid. H2S2O5 is pyrosulfurous acid. And H2S2O4 is thionous acid. So the structure of H2SO3 is this one here. This is also tetrahedral geometry, but one position is occupied by a lone pair. There is one SO bond and two SOH bonds. So this is sulfurous acid. If we draw the structure of thionous acid, H2S2O4. So two sulfurs, two oxygens, that means two SOH bonds and two sulfur oxygen bonds, sulfur doubly bonded with oxygen here. So this is H2S2O4. And for pyrosulfurous acid, H2S2O5, this would be the structure. All right. Coming to the sulfuric acid series, the first is sulfuric acid, H2SO4. The structure of sulfuric acid is this. So tetrahedrally bonded, two S double bond oxygens and two SOH bonds. So this is sulfuric acid. H2S2O7 is also called oleum or fuming sulfuric acid. Fuming sulfuric acid. Now, if oleum is dissolved in water, it gives us 2 moles of H2SO4. And this is the particular reaction that is used in the contact process for the manufacture of H2SO4, which we will discuss in the next class. The structure of oleum is this one here. So here there is a bridging oxygen bond. There's a bond between between the two sulfurs here, and rest of the bonds are S doubly bonded to oxygen. So 2 here and 2 S double bond over here, and 1 SOH on this sulfur, 1 here. Alright, so this is the bonding in oleum. In H2S2O3, this is thiosulfuric acid. One sulfur is bonded to 3 oxygens. This sulfur is doubly bonded to this sulfur here, and we have 2 SOH bonds. So sulfur doubly bonded to sulfur, this sulfur doubly bonded to oxygen, and SOH bonds here. This one is thiosulfuric acid. Coming to the last, which is the thionic acid series. So H2SXO6. This is the thionic acid series. So X can be 2, H2S2O6, then we have H2S3O6, H2S4O6, H2S5O6. Right. So here they are named by the number of sulfur atoms. So this is dithionic, this is trithionic, this is tetrathionic acid, and this is pentathionic acid. So how do you draw the structure? If we talk about pentathionic, 5 sulfur in a line, alright, the terminal sulfurs will contain 3 bonds to oxygen. One of these would be an SOH bond, rest would be sulfur doubly bonded to oxygen. So this is the structure of pentathionic acid. For the remaining, you can just write whatever sulfur are there in the middle, bonded to the terminal sulfurs, all having bonds to oxygen. So this is how you draw the structure of the thionic acid series. Now quickly coming to the questions. This question came last time in the exam, NEET 2023. So you were given the names peroxodisulfuric acid, sulfuric acid, pyrosulfuric acid, sulfurous acid. So to solve this question, you just need to know the formula for this, alright? And based on the structure that we just studied, we can figure out which one contains how many SOH, how many S doubly bonded to oxygen, and how many SOS bonds. So SOS bond is present in oleum. Oleum is pyrosulfuric acid. So SOS here, alright. Now we have SOOS bond. This has to be in a peroxo acid. So peroxodisulfuric acid contains this one. Okay. Now for sulfuric acid H2SO4, in H2SO4 we have 2 SOH, 2 SO. And sulfurous acid contains 2 SOH and 1 SO, because one position is occupied by a lone pair. So this is this question. Which of the following oxaloacid of sulfur has OO linkage? OO linkage has to be there in a peroxo acid series. So which out of these is a peroxo acid? This was an easy question because they gave you the name also, so you didn't have to draw the structure. So peroxodisulfuric acid is the answer. Now oxidation of thiosulfate by iodine gives. This is an application based question. So thiosulfate ion is S2O3 2-. On oxidation with iodine, in the estimation of ozone, we get S4O6 2-. So S4O6 2- is from the thionic acid series. So this is a tetrathionate ion. So the answer is this one, tetrathionate ion. Because this is from the thionic acid series, the ions formed in a thionic acid are thionate. The acid which has a peroxo linkage, again similar question, The answer here would be Caro's acid. Okay, because peroxomonosulfuric acid is called Caro's acid. So with this, questions end. Thank you so much for watching. We'll meet now next Saturday and we'll complete the oxygen family. Thank you so much.